Hello and welcome back. In this video, we're going to take a look at some of the concepts and calculations that go with electromagnetic induction. And we will be filling out our notes and our examples that go along with this particular section. Let's begin. Section 18.1, Inducing an electric current. What does it mean to induce EMF or induce current? Well, inducing an EMF means to simply generate a potential difference and a current without a battery. That is the key phrase right there, without a battery. Fill in the table below in which you describe situations in which a magnet can induce a current in a wire loop and situations in which a wire cannot induce current within a wire loop. So when can a magnet induce current and when can a magnet not induce current? This is a typo right here. This should say magnet. Okay, so we have a bar magnet right here, and you're essentially going to bring this bar magnet in and out of this loop like this. You're going to pass it through the loop. Okay. Now, as we do that, okay, some things were discovered to happen. Well, one, we can induce current if the magnet approaches the loop. So in other words, I'm going to draw in front of this magnet the magnetic fields that are associated with it. And of course, they wrap around to the other side, so I'm just going to draw them as magnetic fields that come into the south pole of the magnet, like this. So the magnetic fields go out of north poles and into south poles. And so what we would have is we would have a situation where if we bring the magnet close, like this, as we approach the loop, we can induce an EMF and thus induce a current. So that's one way. Another way is if the magnet is pulled away from the loop. So in other words, if we take our magnet and we pull it through the other way like this, or we just simply pull it away like this, pulling it towards the loop or away from the loop can induce an EMF and thus a current. Taking the magnet and rotating it near the loop will also accomplish this. So taking our magnet and rotating it like this will also induce an EMF and thus a current. And lastly, if we change the area of the loop, we can also accomplish this. So if we take our magnet here, but let's say we take our loop and we make the loop bigger, or smaller. So changing the size of the loop, thus changing the area of the loop in which the magnetic field is passing through, can also induce an EMF and thus a current. What cannot induce an EMF and a current would simply be taking the magnet and holding it motionless. So a motionless magnet will do absolutely nothing. So it was discovered that electric currents generate magnetic fields. Well, it was discovered some decades later that apparently changing magnetic fields can also create and generate, and the word that we use for it is induce an electric current. And these are the ways in which that was discovered to be done. Now let's take a look at what if we have a situation where we have a primary coil, we have an electric circuit, a battery, hooked up to a switch, so we can, in the primary circuit right here, we can control the current. And you can see the current is going to, once we close the switch, the current is going to go through the wire this way, through the wire, up over this way, 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 and then finally back around to the battery again. So that's the way it'll appear. And you have this secondary coil, which is going to receive the magnetic field coming from this. Now, one of the things we talked about in our last unit on magnetic forces and using right-hand rule, we talked about a concept of a solenoid. So let me remind you, because this essentially is a solenoid. A coil is a solenoid. And so when you have a solenoid, okay, and you have it wrapped around something like this, and let's say the electric current is going up across this way like this, up across this way like this. You take your right-hand rule, okay, and what we do is we take our right hand and our right thumb would go over the top. Our thumb would go over the top into the page, essentially. And what that would do is that would curl our fingers this way. Our fingers would naturally curl to the left. And the summative effect of the magnetic fields curling to the left would send the magnetic field going all the way through the left. And the same is true with this right here. So you can see the magnetic field, or the electric current, excuse me, is going across this way. So if we put your thumb in this direction right here, and your fingers would naturally curl underneath it, like this, going straight down this iron bar. And so the magnetic field will go that way through the coil. Magnetic fields either go one way through the coil or the other way. They pass essentially through the middle of the coil. The direction that the magnetic field goes through the coil depends on the direction of current in the coil. And thus, can figure it out using right-hand rule. Okay, now in this situation, we're going to fill out the table below describing situations in which the primary coil can induce a current in the secondary coil, and which situations that cannot. So a primary coil can induce current in a secondary coil if the switch is closed. So think about it this way. As soon as we close the switch, by closing the switch, current and magnetic field both increase right there on the spot. Current and magnetic field increase as soon as you close the switch. Therefore, we saw earlier that if we take the magnet and we pass it through the loop, you're kind of increasing the magnetic field lines that pass through the loop as you approach, okay? As you approach, because that was one way that we established we could generate induced current. Well, same way here, we can generate induced current from a primary coil to a secondary coil by simply turning on the switch. That increases the electric current in the primary coil, thus increasing the magnetic field that passes through both coils. The second way we can induce current in a primary coil, in the secondary coil from a primary coil, is the switch of the primary coil is then opened. So simply closing the switch increases the current, and then when you open the switch, the current shuts off, which means the current and B field, magnetic field, will immediately decrease. Okay, so the key common point that you should see between a bar magnet and a coil is increasing the magnetic field lines in a loop can induce a current. Decreasing, pulling it away, decreases the magnetic field lines passing through a loop. So increasing them or decreasing them seem to do the trick. What cannot induce current would be if the switch of the primary coil stays on so that no current is passing through the coil. So if it stays open and there's no current, there's no magnetic field, then there's obviously no changing magnetic field, thus no induced current. The other way is to simply have the primary coil, the switch closed, and the current reaches a steady state, meaning the current is not increasing nor decreasing, which means that the magnetic field is a constant value, not an increasing or decreasing value. There has to be a change in magnetic field in order to induce current. So what are some general conclusions that can be described here? Motion. Motion is not necessary to induce the current, but what we have is the number of field lines that pass through the coil of an area. As the area changes, there is an induced current in the coil. So now let's give this an actual name, instead of calling it field lines through a loop. Section 18.2, magnetic flux. Well, what is magnetic flux? It's the number of field lines that pass through the area of a particular loop. Now, we're going to define something here. If you look at the picture, you have the field lines that are passing in some direction through the loop, and you have the area, the flat plane of the loop, which is the area, and you have this thing called the area vector. The area vector is really, if this is the plane of this, it's really the normal. It's really the normal to the plane of the loop. So the area vector is also referred to as the normal vector. Okay, and theta represents the angle between the normal vector and the magnetic field that passes through the loop. So what is the equation for magnetic flux and the units and symbols and variables involved? Well, the variable is the Greek letter phi, and phi is equal to B times A, that's field times the cross-sectional area, times the cosine of the angle between them. Now let's say we had a loop that was horizontal loop. We had a loop like this, and we had field lines going straight through, perpendicular to the plane of the page. Now what do we have there? Here's your plane. Here's your normal vector. And thus, if the normal vector and the B field are going the same way, that means theta is 0. And if theta is cosine of 0, is equal to 1. So phi equals B times A, flux. And instead of saying phi, I'm just going to say flux. This is magnetic flux. Flux is equal to field times area when it passes perpendicular. So this is going to be a nice shortcut that we're going to use most of the time. But if the field ever approaches the loop, the plane of the loop at an angle, then you need to use the cosine of that angle. So let's break down all these. We know that phi is the magnetic flux, and the unit for that is in Tesla meter squared, or WB, which is pronounced Weber. W-E-B-E-R. Weber. B is still the magnetic field in Tesla. And A is the cross-sectional area of the loop in square meters. Again, the area vector refers to, since it's always perpendicular to the plane of the loop, it really also refers to the normal vector, okay, the vector that is normal to the plane of the area of the loop. What is necessary for an EMF and a current to be induced in a wire? You must have a changing magnetic flux through the loop. Section 18.3, direction of induced current. Explain Lenz's law. Well, we'll explain it now, but it's going to make more sense when we apply it. Let's begin. Lenz's law is stated this way. The direction of an induced current is such that the magnetic field, there's a typo here, should say opposes there we go, opposes the change in the magnetic flux through the coil's area produced by other objects. Now that's a very wordy description. Essentially, we can break it down like this. If flux increases, the direction of the induced current's B field leads to a decrease in flux. If flux decreases, the direction of the induced current's B field leads to an increase in flux. Now, let's apply it, and the idea of opposing magnetic fields, okay, and thus opposing fluxes, hopefully will make a little more sense. Let's take a look. The north pole of a magnet moves toward a wire loop. Let's look at this picture here. On the 3 dots, draw the magnetic field vectors due to the magnet. Well, remember, magnetic fields always go from north to south. Therefore, I can draw the magnetic field going down. Going down through the loop like this, passing through those 3 dots. Okay, and what can we say about it? Well, the magnetic field is downward, I'll just say down, and it is increasing. Remember, the magnetic flux is the number of field lines that's passing through the loop. So if the magnetic field is approaching the loop, that means the number of field lines that pass through the loop get bigger and bigger. Thus, the flux is increasing. Now, here's how Lenz's law works. Lenz's law works such that if the flux increases, this is, by the way, known as the external flux. The external flux. And we would just call it flux external, okay, which corresponds to B external, the magnetic field. Okay, they're not the same, they relate. Remember, flux is equal to field times area, okay, but they relate to each other. So external flux refers to the flux and the field that come from a magnet or some source of magnetism. Now, when the external flux increases, the induced flux will oppose this, and I'm going to draw this in blue. So if the external flux is pointed down, increasing flux means that the induced flux that is generated by this loop will oppose this external flux and will go the opposite way. So let's go ahead and draw arrows that are pointing up instead of down. Okay, now that would be the direction of the induced magnetic field or the induced flux. This is the induced flux, which I'm going to call flux IN, or flux induced. This is external flux, this is induced flux. Now, if we take our thumb, if we take your fingers, okay, and wrap your fingers through the loop like this, put your fingers through the loop, your thumb of your right hand will naturally be going in this direction right here, counterclockwise. Thus, the current, the induced current, is CCW, counterclockwise. Okay, and it would just keep going around that direction there. Now, look at what we have here. We have a situation where the induced flux opposes the direction of the external flux. Now, what does that mean about forces involved? Draw the direction of the magnetic force on the magnet and the direction of magnetic force on the wire loop. So let me remind you about magnetic interactions. If we have a bar magnet, okay, north and south, and another bar magnet south and north, well, the magnetic fields go into south poles. Thus, these two magnets, they repel each other. They want nothing to do with each other. Same thing here. The magnetic fields come out of north poles just like they go into south poles. And so if I were to take the north end of this magnet and no, it is repelling, yeah? So if the magnetic fields go in opposite directions, the magnetic forces repel each other. What if we turn it around? Well, if we turn it around, now we're talking about fields that go from north to south, building a bridge of attraction. So when the magnetic fields are pointing in opposite directions, then they repel each other. When the magnetic fields are pointing in opposite directions, they repel each other. When they're pointing in the same direction, okay, notice the north goes right into the south. If it's pointing in the same direction, then they attract each other. Okay, and so here's what we end up with. We have two fields. The fluxes are in opposite direction, therefore the fields are in opposite direction. Therefore, they are attracting each other. This means the magnet, the force on the magnet, is attracting itself to the loop with equal and opposite force. So the force on the loop is pulled up and the magnet is pulled down. We have an attraction there. I'm sorry, I misspoke. They would be in opposite directions, therefore you would see this repel from this, and they would point in opposite directions. I apologize for the confusion. Now the north pole of the magnet moves away from the wire. Well, if it moves away from the wire, then what do we have? We have field lines going into the south pole like this. But since it's moving away, the magnetic flux is down, but it's decreasing since it's moving away. Now, what are the key differences here? When the flux increases, the induced flux opposes the external flux. But when the flux is decreasing, it will essentially replace it and go the same way. So the induced flux also will be pointed downwards because it's essentially replacing the loss of the external flux. And if we use right-hand rule, put your fingers right down the middle of this loop. That would show you that your thumb will go in this way in a clockwise manner. And induced current in this case is clockwise. Since the fields are going in the same direction, what that would show you is that the loop and the magnet would attract each other. And essentially, the force on the loop would be pulled towards the magnet. And what that would actually be in real life is if you dropped the magnet through the loop, it essentially would slow down. Now, the longer the loop is, the more you would be able to slow it down for. Or I shouldn't say the longer, the thicker the loop is, the more you'd be able to slow it down for. So, so far we've looked at what happens when we increase flux, and the induced flux opposes the external flux. And then we've seen also when the flux is decreasing, we've seen that the induced flux points the same direction as the external flux. And those are really your two situations. So let's examine how they would look in other possibilities. We're going to take these same two situations and we're going to apply them in other ways. So how about if the south pole of the magnet moves towards a wire? Well, draw the field lines coming in. Now, the direction of the magnetic flux is up because it's pointing towards the south pole, but it's increasing because you're approaching the loop. Which means if it's increasing, our induced flux, this right here, this is flux external. our induced flux has to go the other way. Has to point in the opposite direction. And if we use right-hand rule, stick your fingers down in the middle of the loop there, your thumb would be going in the clockwise direction, which means induced current is clockwise in this situation. Since the fields are pointing in opposite directions, that means these would repel each other, and the force on the magnet would push down and the force of the loop would push up. They would essentially repel each other. Well, what if we have that the north pole of the magnet is moving away from the loop? Okay, so we have the external flux approaching the north pole of the magnet, but it's going away. So it's directed downward, but it's decreasing because it's passing farther away from the loop. Now, if it's decreasing, we replace the decreasing flux with an induced flux that goes the same way. Think of it like conservation of flux. The total amount of flux has to remain constant. So if we increase the flux, we have to oppose that with a flux going the opposite way. If we decrease the flux, we have to replace it with flux going the same way. Now, put your fingers through the loop straight down. Your thumb would pass clockwise with induced current. So IN is a symbol for induced current. And in this case, it would be clockwise. Since the vectors are pointing the same way, the loop and the magnet would attract each other the same way they did before, pointing towards each other, which again, just like we saw in the previous example, with the forces pointing in, notice how the forces are always going to be pointing in opposite ways, whether they're repelling or attracting, and what that does is that serves to slow down the magnet as it's being dropped through the loop. Okay, now let's take a look at primary coil and secondary coil. It's going to work very similar, but let's take a look. The switch has just closed so that the current in the right loop is beginning to increase. Here's what I would take a look at, and I'll color it a little differently so you all can see it. So as soon as we close the switch, the current is going to go from the positive side, loop all the way around to the negative side. So it will go up, over, through the loop like this, and back to the negative side. That would be the primary current. Okay. Now, if we stick stick your thumb up over the top, or even you can stick your thumb down this way. Stick your thumb down this way. Your fingers would naturally curl through the middle of the loop going to the right. And that same field would pass through that secondary coil to the left. So this is the loop that's producing the magnetic field, but that same magnetic field is going to pass through that other loop. This is my B external, and it's going to match with my flux external. So I'm going to draw my field lines as such. Okay, so this is my external flux relating to my external magnetic field. Okay, the magnetic field in the left loop is directed to the right, and because the current is increasing, so current and flux are increasing. And the reason we know that is because by turning on the switch, you just went from zero current to some current, which means the current increased. So it's directed to the right and it's increasing, which means if the flux increases, then if the external flux increases, then that means the induced flux, which would be passing this way, will oppose that direction. There's my induced flux. And if we take our fingers, wrap it through the secondary loop right here, put your fingers right through the middle of the secondary loop, your thumb would be naturally going over the top like this in this direction. Current would be going up in the front and back. And across the resistor, it would keep going down like this, and the current would pass across the resistor in this way. So induced current passes from right to left across that resistor. What are the forces going to be? Now notice the magnetic fields are pointing in opposite directions. So what does that tell you? The two loops, right, are going to be pushing each other away. Okay, now the switch has just opened, which means the current in the right loop, the current is just opened, so that the current in the right loop is beginning to, this is a typo, beginning to decrease, not increase. We already looked at increase. So we're going to open the switch, and as soon as we do, the current's going to shut down to 0. So the current is still pointing the same way, and thus the magnetic field is pointing exactly the same way as it was before. And this would be my external flux. But my external flux, my external flux and my current are decreasing this time. So the direction of the flux is still to the right, but this time it's decreasing. Now, if that's true, on the left loop, what would this mean? If it's decreasing, that means the direction of the induced flux goes the same way. So let's draw it also going to the right. And this would be our induced flux. Now, in the secondary coil right here, stick your fingers through the loop. Your thumb would naturally be going straight down, which is the direction of the current, would go straight down. Follow that. It would mean the current would go from left to right across that resistor. Since the external and induced flux are pointing the same way, those loops would find themselves attracting each other. Section 18.4, Faraday's Law of Electromagnetic Induction. Faraday's law basically states that a changing magnetic field causes or induces an EMF and thus a current. So in this section here, we're going to state Faraday's law in terms of an equation, and we're going to explain what each of the variables mean. We can write the induced EMF as the epsilon with a subscript IN for induced. And it's N delta phi, which is delta flux, over time. Now, you can put absolute value bars, and I think that'd probably be wise. Put absolute value bars for those. That way the direction of the change in flux doesn't really matter. We're looking at the magnitude of the induced EMF. We can also rewrite that, of course, as delta flux as delta BA cosine theta, where epsilon IN, induced EMF, in volts. Phi is magnetic flux in Tesla meter squared. B is magnetic field in Tesla. A is the cross-sectional area in meters squared. And angle, theta, is the angle between the B field and the normal vector to the cross-sectional plane of the area. Delta t is, of course, time. Section 18.6, changing magnetic field magnitude and induced EMF. Let's take a look at this example. A square loop of wire is in the vicinity of a long cable carrying a current I, which varies with time. When the current is positive, the current has a direction shown in the diagram, meaning to the right. So to the right is positive, to the left would be negative. The diagram below, to the left, shows the cable and the loop, and the graph to the right shows the current in the cable as a function of time. Between which two times on the graph is the induced current in the square clockwise? Explain. So here's how we can figure this out. If we were to take a look at the time from 0 to 1 seconds, so I'm going to break these down into various time intervals. Okay, there's time interval 1, there's time interval 2, time interval 3, time interval 4, time interval 5, 6, and 7. Okay, let's take a look at them one at a time. In time interval 1, and I'm going to take some notes on this up here out of the way. In time interval 1, the current itself is decreasing. So if the current in the wire is decreasing, that means if the current is decreasing, the flux is decreasing. Okay, so now normally the current, if the current is passing to the right, using right-hand rule number 2, we would have our hand firmly down on the table. We would have knuckles below the wire. And we would have fingertips above the wire, including through the loop, which means if we put our fingertips through the loop right here, our thumbs would be going in this direction here. So the current, the induced current goes the same way. So when the flux, and I should specify, as we did in the previous lesson, when the external flux from the current carrying wire source decreases, well, that means that the induced flux in the loop is going to go the same way. And which way is it going? It's going out of the page. Okay, so if we were to reason that out, you can see that the current that we just highlighted here is counterclockwise. But we were told that when the current is positive, right here, the current is flowing to the right. And we want to know between what two times is the induced current clockwise. Well, this is counterclockwise, so that's not it. It's not time interval 1. Time interval 2 during time interval 2, you're going from 0 current to maximum current. So you're clearly increasing your current. Now you're increasing your current the other way. You're increasing your current going this way. Okay, but the current is still increasing. So the current increases, which means the external flux increases. And if the external flux is increasing, and it's increasing which way? Into the page. Okay. Why is this true? Because if we use our right-hand rule number 2, our knuckles would be into the page right here, and our fingertips would be down here. So if the current is increasing, the external flux is increasing into the page, this means that the induced flux must be pointed out of the page. It has to oppose. And if the induced flux is pointing out of the page, like these dots are showing, then that means you stick your fingers through the loop in the direction of those dots so that your fingertips are coming up through the middle, and that leaves us with, again, a counterclockwise current, right? But we want a clockwise current, so time interval 2 is out. So far, time interval 1, 2, they don't fit the scenario. Let's take a look at time interval 3. Time interval 3, you're going from maximum current to no current. So in time interval 3, the current decreases, which means the external flux decreases going out of the page, going into the page. This means that the induced flux is going and replacing it into the page. So if I draw that and I put my fingers going into the loop, that would give me current that is going clockwise. So far, this is showing me clockwise current. This was counterclockwise current. This was counterclockwise current. But this is showing me clockwise current. Let's take a look at number 4. Number 4, you're going from 0 current to maximum current, so you're increasing. Our current is increasing, which means external flux is increasing. And it's increasing which way? Well, it's positive current now, so now it's going to the right, which means we're talking about fingertips coming through the loop, not knuckles. And if we do that, we put our fingertips through well, actually, let's finish this. If the external flux is increasing, that means the induced flux, this would be out of the page. That means the induced flux is pointing into the page. And if I put my fingers into the page, into the middle of the loop, that gives me a clockwise current. So far, time interval 3 and 4 are both giving me clockwise current. Let's take a look at 5. Time interval 5, you're going from maximum current, maximum positive current, to 0 current. So we have current decreasing, which means external flux is decreasing. And what that means, and it's decreasing out of the page. So what that means is the induced flux will also point out of the page. Put your fingertips through the loop out of the page, that gives you counterclockwise current. Okay, and we'll take a look at time interval number 6. I think you're getting the hint here. I'm going to show you a little trick to this in a second, but let's see if you can figure out the hint before I share that with you. In time interval 6, you're going from 0 current to maximum negative current. So the current is decreasing. The current is not decreasing, the current is increasing because you're going from 0 to maximum. So the current is increasing. The flux, the external flux is increasing, which means the induced flux is going to point in the opposite direction. So which way was the external flux going? Well, we're talking about a negative, right here, negative pointing current, which would be fingertips below, it would be knuckles above, and we have to oppose that since this is into the page. The induced flux would be going out of the page. Put your fingertips up in the direction of the induced flux dots. That would give you counterclockwise current. Okay, and I'm not going to count time interval 7 in this at all because it doesn't really finish the time interval. So I'm going to go ahead and stop here. So which times the induced current is clockwise from 2 to 4 seconds. This corresponds to positive slope of a current versus time graph. Okay, so there's the trick right there. Negative slopes, counterclockwise current. Positive slopes, clockwise current. Kind of a nice, easy way of shortcutting through that. Now suppose the cable alternates between specific values of negative 10 amps and 10 amps. We'll say the square itself is 1 centimeter on each side, 0.01 meters on each side, and is located 0.2 meters away from a cable, and that the square itself has a resistance of 0.001 ohms and consists of 200 loops. What is the maximum strength of the magnetic field passing through the square? So B max is going to be equal to I naught, wrong variable, mu naught I max over 2 pi r. So it's still our magnetic field equation. We're just relating the maximum field to the maximum current. That's all. And so we're going to recall that mu naught is 4 pi times 10 to the negative 7. And I max is 10 amps. Whether it's 10 or negative 10 doesn't matter because we want to know the maximum strength, so we're looking for the magnitude only. Divide that by 2 pi times the radius. Now the r is the radial distance away from the cable, so that would be 0.02, or 0.2 rather, meters away. This cancels, and if we plug that in our calculator, we get roughly about 1.0 times 10 to the negative 5 Tesla. Okay. Now, part C, we want to calculate the average EMF and the average current induced during the first 2 seconds. So we're using Faraday's law of N delta flux over delta time. Okay, so the first thing we probably want to do is we want to figure out what the, let's figure out what each flux is. So to figure out delta flux, let's figure out flux initial and flux final. Let's figure them out first. So the field is 1.0 times 10 to the negative 5 Tesla times, and we never calculated the area. So the area, we're talking about a square here. So the area would be 0.01 meters squared, because it is a square, which is 0.0001 square meters. So 0.0001, and let's see, 1.0 times 10 to the negative 5, and we multiply that times 0.0001, and we get about 1.0 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.0 times 10 to the 9 Tesla square meter. And then same thing here. 1.0 times 10 to the negative 5. Okay, but here's the difference. The final flux really is just opposite in direction, simply because you're going from positive current to negative current. When you reverse directions, you reverse flux. So it's kind of a negative, if you will. So negative 1.0 times 10 to the negative 9 Tesla square meters. So if we put that in there, N is 200 turns times, and if we're taking this minus this, it's really just 2 times that. So 2 times 10 to the negative 9, all over, we had a time of 2 seconds. So times 200 divided by 2. It's about 2.0 times 10 to the negative 7 volts. And for the induced current, that's pretty easy to find. Induced current is just induced EMF divided by the resistance. It's Ohm's law. Just use Ohm's law. So 2.0 times 10 to the negative 7 volts over the resistance of 0.001 ohms is about 0.0002 amps, which is 0.2 milliamps. Section 18.7, changing area and induced EMF. In this example, we have a wire that's bent into 3 sides of a rectangle as shown in the diagram. The wire is immersed in a uniform magnetic field B that is directed into the page. Actually, that's a typo. That certainly looks like out of the page to me. Let's correct that. The bar is set on two parallel sides to create a rectangular circuit of height length L and width x, as shown in the diagram. As the bar is pulled to the right by an external force, so the bar travels with speed v. Okay, so in other words, what we get is we get this. If we pull the bar with an external force like this, you can see that there's more field lines passing through the loop. Right now you see there's 9 field lines coming out of the page. Here there would be 12, here there'd be 15. So by doing this, you would be increasing the flux, essentially. Part A. When the bar moves, the area through the rectangular circuit and therefore the flux increases with time. Use Faraday's law to derive an expression for the EMF induced in the bar in terms of the bar's speed, length, and magnetic field. Well, we know that induced EMF is equal to N times the absolute value of delta flux over delta time. It's the rate of change of flux, how quickly the flux is changing. Now, delta flux, what's actually changing here? The area is changing. So this is B times delta A, or the change in area. Okay, this would be delta A right here. So we can write this as an N, we can make 1 because it's really just one rectangular loop. So this ends up becoming B times delta A over delta T, which is B times, now delta A, the changing area, would be length times width. So it's V delta T times L divided by delta T. You can see the delta T's cancel, leaving you with B, L, V, which is another way of writing motional EMF. We get the same thing. Use Lenz's law to show the direction of the induced current around the rectangle as the bar moves. Okay, let's talk about our steps. First, we want to know if the flux is increasing or decreasing and which way. So the external flux is increasing out of the page. We start there. This means that the induced flux must be now pointing into the page. Anytime you're increasing, your induced flux points the opposite way. So into the page means we stick our fingers into the loop, and if we do that, our thumb would naturally go in this direction here as we work our way around the loop, and you can see that is in the clockwise direction. In part C, explain the direction of induced current in terms of free charges in the bar. So this is kind of another way to look at it. Let's take a look at a picture. So we have a bar, and as we apply the force to move the bar to the right, something begins to happen. Okay, and if we use right-hand rule number 1, what that shows us is you put your fingers coming out of the page. You put your thumb in the direction of the velocity of the bar, which is to the right. So if your fingers are coming out of the page and your thumb is to the right, you can see your pencil tip is pointing straight upward. Now remember, we're talking about free electrons here. The charges are electrons we're talking about. So the electrons, if you have the pencil tip out of the back of your hand, the electrons are forced upwards like this. And what you start to see is an accumulation of negative charge. And since the positive charges don't move, the other half of the bar becomes relatively positive, setting up a potential difference. If a potential difference is set up, an electric field is set up. And since the electric field is set up, we now have an equal and opposite electric force to this magnetic force. So again, let's summarize. Use right-hand rule number 1 to find the direction of the free electrons in the bar. We did that, and the magnetic force is pointing up. Number 2, the magnetic force on each electron is directed upwards. This results in an accumulation of electrons near the top of the bar. With positive electrons and negative electrons at the bottom and top of the bar respectively, an electric field is established, directing an electric force to oppose the magnetic force. An electric potential difference is then produced between the top and bottom of the bar. How does this have anything to do with induced current? Well, the induced current will be the conventional current that opposes the direction of the electrons. So you can see the electrons would be forced upward. Well, the conventional current would go downward across the bar in the clockwise direction, because conventional current goes opposite to electron current. Part D, what is the strength and direction of the magnetic force on the bar as it moves? Well, we're talking force equals BIL, which is B times the induced current times L, which again is going to be upward, pointing upward. Magnetic force will be upward using right-hand rule number 1. In the next example, it says a diagram shows a single circular loop of radius little r placed halfway in and halfway out of an into the page magnetic field, B. The resistance of the loop is capital R. Suppose the loop is moving so that an average counterclockwise current is induced in the circle. A. In which direction must the circular loop move in order to induce a counterclockwise current? So in other words, the question wants to know, if we take this circular loop, which way does it need to be moving? Out of the loop, decreasing flux, or into the loop, increasing flux? Let's first take a look at what happens if we move it into the loop and increase the flux. And let's see if that results in a counterclockwise current. If we pull it into the loop, we have an increasing external flux, because you go from half of the field in your loop to the full field in your loop. So if the external flux increases into the page, this means the induced flux will be going out of the page. If, and I'm going to pull this inside, if we take a look at the induced flux as represented by these blue dots going out of the page, take your right hand, take your fingertips, stick them out of the page in through the middle of this loop, and you can see that this does indeed result in counterclockwise current. Therefore, the loop must be pulled into the field. Part B. In terms of little r radius, B, the magnetic field, big R, the resistance, and I, the current, calculate the time it takes for the loop to move the half circle width necessary to induce the average current I as indicated above. Well, in this scenario, the flux doubles. That's your change in flux. Your flux is going to double because you start with half the flux going through to the full flux going through. Therefore, the delta flux is going to be 2 times B times A. And don't forget A is that of a circle, pi times little r squared. So if we take a look at this, we have induced current, I, which I'm just going to write as I. I don't need to write it as induced current because it's telling us what variable to use. So I is equal to the induced EMF over delta T, and we're looking for delta T. But that's also, if we solve for this, the induced EMF is equal to IR. Okay, and don't forget that the induced EMF is also equal to delta flux over delta time. So putting these together, I times R equals delta flux over delta T, and delta T is equal to the change in flux over I times R. Now we just need to write this in terms of more appropriate variables, the ones listed here. And this would change to delta T is equal to delta flux would be 2 times B times A over I times R. Okay, and what is A? This is the same thing as 2 times B times pi r squared over I times R. And one thing to kind of actually to look at this a little bit more clearly, this would be the full area of the circle. So what you actually have, if you looked at it more carefully, is you have half the area of a circle, which is pi r squared over 2, and then to double that means you would get the full area of the circle. So we really don't need the 2 out in front because it's really 2 times pi r squared over 2. Right, which is just pi r squared. So B times pi r squared over IR would properly represent the time. Section 18.8, changing orientation and induced EMF. So in this example, an electric generator consists of a set of coils that have a radius 0.05 meters situated between 2 strong magnets. The magnets have approximately uniform magnetic field between them of 0.1 Tesla and can be rotated. Suppose that the electric generator creates an alternating current with a frequency of 60 hertz and a peak voltage means maximum voltage, of 150 volts. In a paragraph, explain how to determine the number of loops the coil must have in order to meet the specifications of the generator. Well, I'm not going to write a paragraph in this per se. I'm going to work the problem with you to show you that if you set the math up correctly, you would then follow it up with sentences. Okay, so here's what we can start. Flux equals, the flux in general equals B external times A cosine theta, where again theta is the angle between the field and the normal vector. Since theta is that angle between the normal vector and B, and it's constantly changing, theta is constantly changing with a constant angular velocity, we can take this constant angular acceleration formula and we can cancel out theta naught, and we can cancel out 1/2 alpha t squared because there is no alpha. And this changes into theta equals omega times time. Now you can simply rewrite this by substituting omega t for theta. Now, if we write it again, we have our induced EMF is the number of turns N times delta flux over delta T. But we can rewrite this. Now, we would rewrite this by using differential calculus. So if you happen to know the derivative of a cosine function, you would know that that is a negative sine function. We're only interested in the absolute value, hence the bars right here. Okay, but if the absolute value of negative sine is, of course, a sine function. And you could, of course, know that taking the chain rule, we would the derivative of cosine omega t would be sine. It would be omega times sine omega t. And so using a little bit of derivative calculus, we would go from here to here. So if you don't know that derivative calculus, and that's fine, you don't need to. I'm just simply showing you the end result. Okay, calculus got you there. So it would be n times b external times a omega sine omega t, where omega is the angular frequency. Okay, now recall that the peak EMF, the induced EMF occurs, a peak voltage occurs when the sine of omega t is 1 and -1, because we're talking about a sinusoidal function like this. And the peak, the maximum amount of voltage you have, is going to be situated at the highest and lowest point of the function, of the sine function. So the induced EMF, the maximum induced EMF, can then be rewritten essentially because sine of omega t is 1, so this whole value essentially goes to 1, and you can write it as simply as n times b external times a omega. Now, we spoke earlier that omega is the angular frequency, which is 2 pi times the actual frequency of 60 hertz. So 60 times 2 pi is 120 pi radians per second. The other variables would be listed here. The maximum EMF is 150 volts. The magnetic field is 0.1 Tesla. The radius of the loop is 0.05 meters, which means the area would be pi times 0.05 meters squared, which is 0.00785 square meters. And we want to know the number of turns that would make this happen. So max EMF, peak voltage, is equal to N B external times A omega. Solve for N. E max over B external A omega. Plug in your values. And we get roughly about 500 turns, a little over 500 turns. Section 18.9, transformers, putting it all together. The diagram shows two coils wrapped around the same iron bar. The primary coil, which is the top one here, has current passing through it, shown in the completed sine graph right here. Draw the current in the secondary bar as a function of time. Note the positive directions of positive current for each coil as shown by the voltage source in the ammeter. Well, here's what we know. The primary EMF is related to the secondary EMF in terms of the number of turns. It's related directly to the number of turns. The primary number of turns versus the secondary number of turns. Now, if you count, you'll see that there are 12 turns in the primary coil and there are 6 turns in the secondary coil, which means there's twice as many turns in the primary coil. If you solve for I secondary, that would be I primary divided by 2. In other words, the secondary current will end up being half of the primary current because the secondary current has half as many loops, which means we would draw the current half as high. So instead of going all the way, we would just go half the way, like this. Something to that effect. The point of a transformer is to essentially increase or decrease the maximum value of this alternating EMF. Section 1810, Mechanisms Explaining Electromagnetic Induction. Explain the duality of varying electric and magnetic fields and the relationship to electromagnetic waves. Well, essentially, what you have is you have changing electric fields which generate magnetic fields that will also end up changing themselves. These changing magnetic fields will in turn, a little typo there, induce further electric fields to be changing. This process keeps going on and on and on. This is known as a self-propagating wave. And this electromagnetic wave, if you recall, is a light wave. All waves of light are electromagnetic, meaning they have electric fields and magnetic fields that essentially produce each other. The changing electric field produces magnetic field, and the changing magnetic field produces more electric field. I hope you found this helpful. Again, please pause and rewind as necessary. Thank you.